New Evinia, and we're back. And yep, so as you can see, today we're going to talk about the basic concept that we need to know for, calculus and all that stuff. Like, because most of the time, some of the teachers will just give you the formula and then just deal with it without explaining why it works. So in this video, we're going to talk about some of the basic concepts that we need to know about calculus. Just in case, I will only cover some of the extremely basic important parts that we need to know in this case. But for the rest of the more slightly complicated stuff, don't worry, the other channels or YouTubers out there or teachers out there will cover it. So in this case, I will only cover some of the extremely basic and important concepts. So without further ado, let's go. So yeah, just in case, in the previous episode, we did talk a lot about slopes in this case, but just a quick reminder, what is slope? Like, if you have a straight line, the slope is actually delta y divided by delta x, where delta y is the change in the y direction, and then delta x is the change in the x direction. So with that, you have slope. But now asking a question is, if I give you any function, well, it's not exactly a straight line, it can be like any weird curvy line, what it is, then the new question will be something like, what is the slope of a function, or what is the slope of a curved line? So that's what we're going to talk about today, and yeah. Alright, so just in case, if you still recall, for a straight line, we have y equal mx plus c. And then, of course, you can just like move around some of the numbers, and then you can just find out what's the slope or whatsoever. Or you can just simply just pinpoint 2 points on a straight line, and then you can just immediately find out what is the slope. But for a curved line like this, or a curved function, or what I would call it, well, situation is not exactly that easy. Like, for example, what is the slope of this thing? Like, is the slope something like this, or like this, or like this, or like this? I don't know. But one thing that we can know is if, like, given, let's say, an x value, like when x is 3, which is somewhere around over here, well then maybe at least I can guess the slope might be something like this. So here's an important hint. So as I move along the line, you can see the slope. Oh, it's okay. So as you can see, as I move along the line, the slope changes. This also means that as my x coordinate changes, my slope also changes. So this also means that we can also draw or plot the relationship between the x value and the slope. As you can see, I'm tracing this very poorly, but I hope it demonstrates the idea. So yeah, the main idea, the slope changes along the y value. Well, theoretically, you can also do something like the slope also changes along the y value, but it's actually much harder because we already set that y is some function of x. But if you were to do it the other way around, then it would be harder. So most of the time we'll just do, when x is a specific value, then the slope is a specific value. So one main key thing is a slope. The slope for a curved line can be treated as a function based on x. Like, as x changes, the slope also changes. Now we're going to take a look how it's like determined or calculated in this case. So yeah. So as you can see, like for example, if we want to know the exact slope when x is 1, which is this slope over here, what we can do is, alright, we need to like, because the slope is based on change in this case, so we will just say, alright, let's change our x a little bit, so we will have an extra length, delta x. And then, of course, this also means that we have our delta y. So now, over here, we have our new point. The approximate slope when x is 1 is delta y divided by delta x. And then you just do the math and then just punch the calculator. Yeah, whatever. But now the problem is, if your delta x is too big, like your delta x is way over there, then maybe your delta y is way over there. Then that is not perfect. Then that is not the exact slope that we are looking for. So the thing we are looking for is we have to squish our delta x smaller and smaller. So let's compare it. Like, take a screenshot right now. So this is the slope right now when delta x is that big. Now let's shrink delta x a little bit smaller. Okay, so there we go. Now I have shrunk delta x a little bit smaller. This also means that, oh wait, delta y is also smaller as well, but the ratio almost is like maintained in a way, and you can see the slope is getting closer to the curve, like it's almost getting to become a perfect tangent. So let's just shrink delta x again and take a snapshot again just to compare like how is the slope like getting improved over here over time. Okay, there we go. Now as you can see, delta x and delta y are actually quite tiny at the moment, but you can see the slope, we're almost getting what we need. So ideally, if we just want the perfect slope at this specific point, what we need to do is to let delta x approach 0. Ow. Okay. My table. Okay, my table's not broken. I'm good. Okay, so in this case, we just need to like shrink delta x such that it approaches 0. Then the slope will approach the tangent or the slope at this point that we want to find. So this is the main key of finding a slope on a curve. So yeah, we have that. Oh boy. So in this case, now we can actually start deriving a formula for the derivative. In this case, the derivative is a function such that it takes x and then it will give you the slope at that point. So in this case, the derivative, I just write it out. In this case, we can note this thing as dy dx. Dx in this case. But most of the time, y in this case is actually just f of x. So yeah, if you haven't watched the previous episode where we talk about functions yet, then go watch it and then come back in this case. So in this case, this just means that, okay, we're going to take the derivative of f for x, but taking x as our input. So in this case, another way we can write this is we will just put f of x on the other side. There we go. So we have that. So in this case, derivative of x is actually just something like, it's going to be a new function such that when I put in a value, it will give me the slope of that x value. Like when x is something, slope is something. So now we can actually start deriving it. So in this case, it's almost the same thing. Delta y divided by delta x. But in this case, okay, I might just call delta x in this case. So delta y, what is delta y? So first we need to know, what is this point over here? So this point over here is actually same function, but okay, let's just say over here is the coordinate x. So the x coordinate over here is x plus delta x. There we go. So we have this. That point over there, that is x. This one over here is x plus delta x. In this case, I mean the x coordinate in this case. Now, the y coordinate over here is y. Oh wait, no. The y coordinate over here is actually f of x. Because the y value is just basically the, just the x value, put it in a function, and then it gives you the y coordinate. So the y coordinate of this point, which is the same as the one over here, is actually f of x. Now, the y coordinate over here is actually x plus delta x, and then you put it through f. So because over here, this x coordinate is x plus delta x, and then you put it into the function, and then it gives you this y coordinate over here. And then for over here, our x coordinate is just x, and then put it through the function, we have f of x. So that's our y coordinate over here. So now we can actually start plugging in those numbers in this case. So delta y is actually f of x plus delta x, and then minus f of x, which is the difference in between the y coordinate in this case. Now, what is delta x? Delta x is just delta x. There we go. I might have write that the opposite way. Never mind, I'll just edit it in the video, whatever. Now, the problem is, delta x is like any arbitrary number. Now, remember the part where we need to like shrink delta x until it reaches 0? In this case, we're gonna do the same thing over here. So, let me make space. There we go. There we go. So now we need to let delta x approach 0. So what we will say is we will have our limit such that delta x is approaching to 0. So there we have it. This is the important general formula for the derivative of a function. So up over here we have our delta y, down over here we have our delta x, but delta x is approaching to 0. As delta x is approaching to 0, we can know our slope is getting closer and closer to the tangent, just like the snapshot that we took a while ago. And then delta y is just actually our new y coordinate minus our original y coordinate in this case. So there we have it. We have our delta y over delta x, where delta x is getting squashed to 0. So yeah, this is our general formula in this case. And then for the rest of the derivative rules, like how will you take the derivative of, let's say, 2x cubed, or maybe something like ln 4 or something, I don't know, or maybe some constant rule or whatsoever. I'll just leave those to the others. So yeah. Alright, so in this case, let's just quickly go through the mathematical function just to find the derivative of a function. So in this case, let's just say our function is, okay, there we go. F of x is 2x squared plus 5x plus 3. So this is our function. So this means that this point over here, the x coordinate is x. And then this red line over here is dx. This one over here is x plus dx, like the x coordinate of it. Now, this one over here is f of x. This one up here is f of x plus dx. So in this case, let's just like figure it out. What is f of x plus dx? So now, this one up here is 2, and then x plus dx squared, and then also plus 5, and then x plus dx, and then plus 3, which is also 2, and then squared plus 2x dx, and then plus dx squared, and then plus, and then 5, and then x, we just do the other, plus dx, and then plus 3. Now, this is also 2x squared plus 4x dx plus 2 dx squared, and then plus 5x plus 5 dx plus 3. Okay, so just let me check that, and then we're good to go. Alright. And then what is f of x? F of x is already given, so we have 2x squared plus 5x plus 3. Now we just need to take the difference, which is the distance along the green line. So in this case, the difference would be, okay, x squared, 2x squared is taken care of, and then we need 5x, so 5x is also gone, and then plus 3 is also gone. So what is left in the middle is 4x dx plus 2dx squared plus 5dx. There we go. And then now we just need to take this thing and then divide it by our dx, because that's the derivative in this case. So in this case, we have 4x plus 2dx and then plus 5. So there we have it. Now we just need to like apply the limits in this case. So when dx approaches to 0, we have 4x plus 5. So there we go. 4x plus 5. What does it mean? If you still remember, derivative is a function such that it takes in a value and then it will give you the slope at that point. So this means that the derivative of our function over here is 4x plus 5. So let's just quickly jot that down. 4x plus 5. So what does that mean? It just means that the slope of our function is 4x plus 5. Meaning the slope changes when x changes. So for example, when x is, let's say, 3, then we can immediately know the slope when x is 3, like at that point, is actually 17 or something like that. And then you can just like you can just give an x value, and then you can immediately know what is the slope at that point. So we have that. So yeah, this is a quick mathematical example just to figure it out what is the slope of a function. So we have that. Alright, so yeah, now if you guys has been into like calculus for a while, maybe you guys have heard of something what is called an integral. So just in case, to quickly explain what is integral is if we have a function, let's say f of x, and then you take the derivative of it. So I'm gonna call it derive it. Then you have a new function. In this case, we normally call this function f prime for x in this case. And then, yep. Okay, so what integral does is it does the total opposite. And then shoop. So yeah. So in this case, we can say the integral is something like an inverse function of taking the derivative of a function. Okay, so we have that. Now when most of the teachers talk about the integral, they will say something like, if we have a function and then you take the integral of it, you will get the area under the curve until the x-axis. And then most of the students will just immediately ask, why? Including me. Now, here's what most of the teachers will say. They will say, okay, let's say we have this like big blob of area covered, and then we will chop them up into hundreds, millions of rectangles, such that those rectangles are so small. And then you quote unquote sum them all up, add them together, and that's the area. Now the missing part is why doing the opposite of derivative, which is integral, will sum them up. So in this section, I'm going to explain it. After all these years, like when I finally understand why it works, it feels good. Yes. So let's go. So first and first, let's call this function f of x. Okay. Now, assume that we have our area over here. Now, let's just say, this thing is not good. There we go. So let's just say this area over here is already known. So we will call the area, or let's just say surface, S in this case. Now, let me see if I can activate this. Toggle line. There we go. So now, it's the same idea in this case. This is our stuff. So when x is a given value, which is this yellow one, our S is this big blob over here. Now we will change our x value a little tiny bit. Okay, so okay. That looks good. All right, cool. So this little tiny change along x is our dx. So we have that. I just need to make sure that I'm facing it the right way. Okay, cool. So that little tiny change over here is dx. This also means that our area has also changed a little bit in this case. So our new little change of area, we can call it ds. So here we have it, which is actually this new area over here. And then if you shrink dx closer and closer to 0, then ds is closer and closer to become a rectangle. And then this rectangle over here is what most of the teachers will just say, it's the rectangle that you end up with if you chop it up many times. But to me, not quite. It's actually just a change of surface or change of area when we change our x a little bit by dx. So in this case, what is the height of the rectangle? The height of the rectangle is actually f of x. But if you want to be extremely strict enough, alright, fine, f of x plus f of x plus delta x, take this whole thing divided by 2, I don't know. But when dx is close to 0, the height is f of x. Now, we can actually, this is where the magic happens. This is where the magic happens. Now we know, wrong side, there we go. Now we know ds x and dx. Now, we can actually understand this in 2 ways. Either we can like integral both sides. Okay, let's do the first way first. Integral both sides. So when we do the integral of both sides, ds becomes s, and then f of x dx becomes f of x got integral respect to dx. So this is one of the reasons why when you take the integral of a function, you will get the surface. Now, another easier way to understand is, if you rearrange this whole thing, you can get f of x is actually ds by dx, which means surface area got derived or got differentiated respect to x, you will get f of x. So s get derivative, like derived or differentiated, you get f of x. What's the other way around? F of x get integrated, you get s. And this is why when you take the integral of a curved function or whatsoever, you will get the area underneath it. Finally, all these years, I hope this helps. Ah, feels good. There we have it. So yeah, we have that. So yeah, just in case, now some of you might asking, okay, why do we need calculus? Why do we need integral? Why do we need derivatives and all this stuff? Well, turns out you can actually use calculus in order to understand why some of the formulas is this. Like for example, what's the volume of a sphere? So we can actually just use that idea in this case. Just let me there we go. Alright, let me adjust some of the stuff. Alright, there we go. So let's just see if we can get the volume of a sphere in this case. So in this case, I'm going to say from here to here is x. Yep, so we have that. So now we can say, okay, let's just say I'm going to slice this sphere in this case. So such that, let's see, there you go. So such that this slice over here to the right hand side, let's just call it V, which is the volume of it. Let's just say magically we know that this slice to that side over here until where x is 0. We know our volume, V. And then we change our x a little bit. Along how much? Dx. And then we will have our change of volume, which is the cylinder in the middle. Okay, so we have this. Now, what's the volume of the cylinder? We know in this case, so we have dV is pi r squared. What is r? We don't know that yet, but we'll take a look at that. And then by our thickness of our cylinder, which is dx. Now, the problem is, how do we know what is our radius is? So, our sphere over here has a radius. Let's just call our big radius r. Big R whatsoever, okay? And then, if we can actually extract, we can actually extract our sphere in this case. So in this case, let me do this. Let me quickly do this. Stand back over here. Yeah, that will do. Okay, let me have a radius of, let's say, 2. Radius. So there we go. Now we have a circle. So now, we know that, let's just say this is the cross section of our sphere. Here is when x is 0. And then over here is when x is 2r. And then let's just say this slice over here is the dV we want in this case. So if we just have our r over here, let me do it real quick. Okay, there we go, and then I'll just, there we go. So there we go. This is our radius. Now, what is our radius of our cylinder? I'm going to take the cyan line in this case. So, push, and then I'll just go. Now, another thing that you can immediately see is, now we have our lovely right triangle. And yes, Pythagoras theorem, let's go. So, now the problem is, what is this red side? So at least we know, from 0 until cyan line is x, and then from 0 until center point is r. So we know our delta x is actually r minus x. So according to the Pythagoras theorem, we can know our cyan line, or the radius of our cylinder, is r squared minus r minus x squared. Correction, small r squared. There we go. This is our small r. So yeah, small r squared is this thing. Then we can come back here, because over here we have dV is pi small r squared and then dx. And then what is small r squared? We have it right there. Perfect. So we have dV is pi and then r squared and then minus r minus x squared. And then this whole thing dx. Does that look correct? Yes, it looks correct to me. Now we are ready to integral both sides. So if we integral on the left side, we have v. And then if we integral on the left side, eventually, okay, just in case, in order to make things faster, actually I have done this beforehand. So let me get my papers. In this case, there we go. So in this case, whoop, there we go. Alright, what you will get is, if you integral the left side, you will get pi big R and an x squared minus 1/3 pi x cubed. And then this means that if you plug in the x value, as long as the x value is in between 0 and 2r, it will give you whatever volume it's to the 0 side of it. And then when x is too big R, you will get the volume of the entire sphere. And in fact, if you plug that number in, you will get the volume of a sphere. And this is where the volume of a sphere comes from in this case. So yeah, we have this. Finally. So for a small exercise, try to find the volume of a cone. So yeah, that's a small exercise. So we have that. So yeah, in this case, we have covered some of the most important concepts about calculus. And then for the rest of the more complicated stuff, we'll just leave it to the others and see if others can help you deal with it. But I would say this episode is meant for like punching down some of the most important part that we need to know and handle, and then the rest will just fall like a domino in this case. So yeah, if you watched the video until to this very point, thanks for watching. And then yes, of course we will work on more episodes just to talk about different stuff in different areas. And then if you go take a look on our website, you can actually take a look at what our roadmap is. And then yeah, so we have that. So yeah, thanks for watching, and I'll see you in the next video. Bye bye.